Hello, in this video we're going to go over a problem from Virginia Tech Regional Math Competition. So here is the problem. Prove that every positive rational number can be written as a finite sum of distinct reciprocals of positive integers. Okay, so as usual, I'll walk you through the process by which I obtain a solution. So first I started with some examples. Let's say I want to write down 3 over 10 as a sum of reciprocals of positive integers. So then what I did was I looked at fractions that are less than 3/10. So the first one is 1/3 that is less than that, or rather 1/4 that is less than that. So 1/3 would be more and 1/4 would be less. So now I'm going to take the 3/10 and subtract 1/4 to see what I get. So the common denominator is 20 and I would get 6 minus 5, which is 1 over 20. So that tells me that I can write down 3 over 10 equals 1 over 4 plus 1 over 20. So that's nice. Then I tried a couple of other examples. Let's say you try 2 over 11. The the reciprocal of integer that is more than that would be 1/5, and 1/6 would be the first one that is less than that. And then I took the difference, 2 over 11 minus 1 over 6. That would give me 12 minus 11 over 66, which is also 1 over 66. But it doesn't make sense that this always becomes 1 over 66. And in fact, that is not always the case. So I tried other examples. For example, if you try 5 over 7, that is between 1/2 and 1. And when you try 5 over 7 minus 1/2, the denominator is 14. That becomes 10 minus 7, which is 3 over 14. Now, can I do the same thing for 3 over 14? Well, I can look at 3 over 14. This is less than 1/3. Is it less than 1/4? It is also less than 1/4. And it is greater than 1 over 5. And then we can do the same thing here. So 3 over 14 minus 1/5 gives me 15 minus 14, which is 1 on top. And the denominator is 70. So from here, we can write down 3 over 14 as 1/5 plus 1 over 70, which means 5 over 7 is 1/2 plus 1/5 plus 1 over 70. And then I thought, oh, can I extend this idea? It looks like maybe I can extend this idea. And here is why I thought this could be extended. So if you look at this fraction, I started with 5. The next fraction became 3. The next fraction became 1. And look at the other examples. I started from 2. I ended up with 1. I started with 3. And I ended up with 1. And it looks like the process that I'm working with is only working for integers between 0 and 1. What if I have a positive rational? So what am I going to do? So let's take some rational that is positive. Let's take the numbers that are the consecutive numbers in the harmonic series and subtract it one after another so that we get something between 0 and 1. So we're going to take this one and we're going to subtract 1, 1/2, 1/3, etc. all the way to some 1 over n. Because this harmonic series goes to infinity, at some point this becomes negative. So let's say this 1 over n plus 1 is negative, and the previous one is positive. So r minus 1 minus 1/2 minus 1 over n is positive. So what does that mean? It means this r is greater than the sum of 1 over k equals 1 to n, and less than the sum of 1 over k equals 1 to n plus 1. So what we want to do is we want to write down r as a sum of fractions of reciprocals of integers. So we can take r and subtract these reciprocals to see what we get. So if you take r and subtract the sum of 1 over k equals 1 to n minus 1, you get 1 over n on this side, and you get 1 over I guess you get this would be 0 on this side, and this would be 1 over n plus 1 on this side. So this number is a number that I would have to show. It can be written as a fraction of, as a sum of two, as a sum of reciprocals of positive integers. So now I was successfully able to take this one and put it underneath 1 over a plus n plus 1. Now let's call this fraction a over b. So now, how do we write down this fraction as a sum of reciprocals of positive integers? Well, we're going to look at a over b. A over b is between two reciprocals, so 1 over m and 1 over m plus 1. I know that. And I know that this m would be at least n plus 1. So now we're going to subtract a over b. So we get a over b minus 1 over m plus 1 is equal to m plus 1 times a minus b over m plus 1 times b. Now let's look at the numerator. What is the numerator? If you look at the numerator, we have m plus 1 times a minus b. That is ma plus a minus b. Now ma from here, we can see that ma is less than b, which means ma minus b is negative. So this numerator is in fact less than a. So I ended up with a fraction that the numerator is less than a. So now I have this one. I have m plus 1a minus b over m plus 1b. And this fraction is less than this numerator is less than the previous numerator, and this fraction itself, the fraction that I have here, is definitely less than 1 over n plus 1 as well, because we subtracted 1 over n plus 1 from a over b. So we ended up with another fraction that is that the numerator is smaller. Now if you repeat this, so we got this. We got a over b is equal to 1 over n plus 1 plus this fraction with a numerator that is smaller than a, n plus 1 times a minus b. Now if you repeat this, and we know that this is less than, even less than 1 over m plus 1, it's less than 1 over n plus 1, which means we can write down this one. If we repeat this, we can write down this one as the sum m plus 1a minus b over m plus 1b as a sum of reciprocals of distinct positive integers more than n plus 1. Why? Because this fraction is itself less than 1 over n plus 1. We saw that here, because if you write down a over b minus 1 over n plus 1, you get this is less than 1 over m minus 1 over n plus 1. And this fraction is in fact less than 1 over n plus 1. Now, if you think about what happened here, was I started from r, I brought it down between 0 and 1, and then I repeatedly wrote down those as sum of reciprocals of positive integers. So that means eventually we can write down r as a sum of 1 over some ki's, and that brings me to the end of the video.